One of the most important things you can do in Yocto is to create a custom layer. A custom layer is a great place to keep things that, say, apply changes to other layers, or you want to install drivers for a default image, or maybe change how the login process works. It's also a great place to keep custom applications, which is something we'll explore in a future episode. But for now, let's just see how to create a custom layer and then use it to create a custom image. The first thing we want to do is look at how Pokey constructs its image. So let's head to our projects, Yocto, and we are going to go into the Pokey reference distribution and go into the meta folder. In there, you should see a folder called classes. We want to view classes and the image.bb class. A BB class is a recipe that's to be used as sort of a template for other classes. It's something you would import. If you're familiar with object-oriented programming, it's kind of like a class in that. This is the main recipe for constructing our image in Pokey. We don't want to modify this because we don't want to modify anything in the Pokey directory or the Pokey layer. What we want to do is create our own layer that's separate from Pokey, that exists, say, in the Yocto directory, that makes modifications to some of these variables. Feel free to scroll through this image recipe just to get an idea of some of the variables that's being used and some of the functions that are being called here as far as do compile, do build, things like that. You are welcome to look up any of these variables and functions on the Yocto documentation to get a sense of what they do. But for now, we're going to exit out of this. We want to go look at the core-image.bb class. If you scroll to the bottom of this, you should see something that says inherit image. That inherits the image class we just looked at a second ago. And it pulls in all of the variables that were defined in that recipe. The other thing you want to note here is this variable called image install. You'll notice that the question mark equals is a soft assign, and that means assign this core image base install variable, which is up here, to this image install. This particular variable includes a number of packages that are needed to get Linux working. In this case, we have package group core boot, which is the bare minimum number of packages needed to get Linux just to boot and give you a console and a few tools with something like BusyBox, if you want to use that. And base extended includes some other packages and tools that we're going to try to avoid. What we want to do is modify this image install variable to include the package group or the only package groups that we care about. Let's quit out of this. And let's head to recipes, core, images, core image minimal. And this is what we have been building. We've been building this core image minimal image. This is what we're going to want to work with. As you can see, it overwrites that soft assignment. Instead of package group core boot and package group base extended, it now just contains this package group core boot, along with this core image extra installs, which I think comes from the board support package. So we'll probably need to keep that in. And in fact, what we're going to do is just copy this entire file, and this is going to form the basis of our custom image. So rather than building core image minimal, we're going to build our custom image, which we're going to name custom image, and it's going to look something like this, and then we can make tweaks to this recipe. For example, one of the things we're going to do is we're going to expand the size of the rootfs. If you're wondering why there was only about a megabyte of space available in the root file system, it's because of this variable right here. This says only make rootfs about 8 megabytes. You'll notice this is not exact because rootfs appends some extra space and it does some wonky things when it's trying to calculate how much space is needed for all of the packages and tools that are required when it's building the image. So it builds that, and then it also says, hey, let's give you 8 megabytes, but it may be plus or minus that depending on what kind of tools and the extra space appended. We're going to modify this and give ourselves, let's say 200 megabytes, but you could change it to 2 gigabytes, 4 gigabytes, take up the rest of your SD card. Just be cognizant that when you do that, you have to copy all X number of gigabytes over to the SD card, which could take some time. So I'm going to do 200 megabytes just to save a little bit of time when I'm copying the root file system back and forth. Finally, the other thing we can do in here is add users, and you can also change passwords. So I'm going to leave that up to you if you want to add a user. I'm just going to change the root password to show you how you might do that so that the root password is changed when you first boot up the device. We'll quit out of here. We want to look at the classes extra users.bb class. We need to inherit this bb class recipe if we want to use this extra users params variable. This allows us to do things like call user add, group add, modify groups, add users, change passwords, and the like. These are very similar to the Linux commands that you would use to add users and change passwords. There are a few slight differences. For example, there might be a capital letter P that you will see that is different from the Linux command, and I will point that out because remember that even though these look like the Linux commands, they're actually Yocto commands. So keep that in mind. Let's head out of this, and we are going to go back into our main Yocto directory. And here we are going to go ahead and enable our environment. So that is just source, pokey, oe, init, build, env, and we're going to go into our build directory when we enable the environment. With this, we have access to all those variables, classes, and more importantly, the bitbake command. Notice here we're in our build mp1 directory. We don't want to put our layer in here. So our layers should exist separately from our build directory. Our build directory should be local only. And then when we create a layer, you will want to do something like put that under repository control, whether it's Git, SVN, what have you. That's what you maintain so that when you go to create your own custom image or build, you pull in your own layer along with the BSP layer, the pokey layer, and then you combine all of those in your build process locally to create your image. We're going to use the bitbake-layers command, and we're going to create a layer. This is going to be our custom layer. And most layers you will find start with the meta prefix. So we're going to call ours meta-custom. So when you see that name, you know we're talking about our custom layer. Now that our custom layer has been created, you should see the meta-custom directory in this top-level directory of Yocto, and we are going to go into that directory. You'll notice that when we called the bitbake-layers command, it created a very simple directory structure for us containing everything we need for our custom layer. As I mentioned, this meta-custom is what you would want to put under version control, so this would become its own Git repository, much like how you saw the BSP from ST was maintained under Git, and that was its own layer. Something we're not going to get into here is maintaining that repository, as what you'll want to do is set up a test structure or a test framework that tests your layer and make sure it's compatible with the various Yocto branches, and you would want to give your layer branches, your meta-custom here branches, similar names. So this branch should be something like Dunfell so that it matches Dunfell on all of the other layer branches. We're going to create a custom image in our layer, and we're going to put it in recipes core. And in that, we're going to create an images directory. I think the naming is important here for these particular names, recipes, cores, images, because that's where bitbake looks for image recipes. I think. I have not confirmed that. As I mentioned earlier, we're going to start with the core-image-minimal recipe for creating an image, and we're going to modify that. So we're going to copy it from the Pokey reference distribution, and we're going to put it into our recipes core, images, and we're going to rename it to custom-image.bb. And one thing I didn't mention earlier was that When you created this layer using bitbake-layers, it creates this recipes example. And you can look inside of this recipes example to see what they provide us. And they give us an example directory in here. So if we go into recipes example, we look at example, and there's a example recipe that you can look at. So we'll take a peek at this. This just gives you a basic template to start writing your own recipes. It has a summary, description, license, some sort of do display banner, and then you can add the task. We're not going to include this recipe in our build, but I'm going to leave it in here so that you can kind of get an idea of what's going on. Feel free to remove recipes example if you don't need it. It's just here for you to look at. Let's go ahead and modify our custom image recipe. So we're going to go to recipes core images and go to our custom-image.bb recipe. Remember that this is something we copied in, so you should see some basic information filled out here. Let's start by changing the summary variable. We are going to leave the image install variable alone because we want it to look like core-image-minimal as much as possible. So we're going to leave package group core boot here and the core image extra install. To have access to that variable, we're going to import or inherit the core-image-bb class that we looked at the beginning of this video. The other thing we want to do is inherit extra users, and that's what I showed you earlier, where we want to import that recipe here so that we can modify users and do things like change passwords. The next thing we're going to do is change the root file system size to about 200 megabytes or 200 mebibytes. It won't be exact because of how the build process calculates the size needed to put all of the tools in, and then it tries to make it the size you specify. It's not exact. One of the things the build process does is it figures out, or it tries to figure out, how much space is required by the main root file system, and then it gives it an overhead factor. So if the root file system takes up 10 megabytes, I believe the default overhead factor is either 1.5 or 1.2, so it adds an extra 2 or 5 megabytes to that size, and that's how much root file system space you get. We can set it manually, and this will attempt to create a size of root file system that is the size you set. But in order to make it that size, we need to set the image overhead factor to 1, where it calculates how much space is required by that root file system size, including all of your packages, and it only allows it to take up at most this space. So if your root file system is going to be more than the space you're providing here, you're going to have to do some calculations, which is why it's generally advisable to let it expand to the space that's needed. But I'm showing you here how you can create a larger root file system to give you more space available when you install Linux on your root file system. Now, for security purposes, you generally want to have a root file system that's just big enough for your kernel, packages, other modules, libraries that you need to get your application running for your specific embedded Linux board. You normally don't want users messing around with root file systems. So if you have some kind of user that's supposed to log into this device, that's why you would give them their own partition that they can make changes to, and only root can change the root file system. But I will leave that up to you, say as a homework assignment, if you'd like to figure out how to add a user and give them their own partition to play around in. For now, let's just leave everything within a root file system. We're going to do everything with root access and pretend that there is no user to log into this device, and it's just supposed to accomplish its task with no users. It just does it automatically, like, say, an IoT device. Now that we've assigned the root file system size, we are going to remove this extra space append since we don't need it anymore. If you want to add users or change passwords or create groups, you can use this extra users params that we saw in the extra users recipe class. Once we import that, we have access to this variable, and we're going to hard assignment. The question mark equals is a soft assignment where it basically assigns this value as a default, and another question mark equals could overwrite it, or a hard assignment, which is this equals, could also overwrite a variable. The hard assignment, which is just a equals, will always overwrite, and whatever the last equals was found during the parsing of all your recipes is the value that's assigned to this particular variable. By using a soft assignment here, we're allowing somebody to make changes in the build directory. Say, remember that build-conf local.conf file that we could modify. Somebody could change these variables there if they wanted to create a different root file system size or assign a different root file system size in order to, say, expand it to the full extent of whatever SD card they have available. But for now, we're going to keep it as a default of 200 megabytes. Similarly, we're going to hard assign this extra user's params variable, and we're going to call this function whenever this parameter gets run somewhere in the bitbake process. It's going to change the root password to Tor, which is just root backwards. We're going to do this with usermod and the -p argument. Normally, usermod uses a lowercase p, but as I mentioned earlier, this is not an actual Linux command, this is a Yocto thing. It looks like a Linux command, but some things have been changed. For example, this lowercase p is now a capital P when we are dealing with root because it makes you realize that you are assigning a plain text password to root or the root account, which is generally not a good security thing. If I check this layer into GitHub, for example, everyone would know, or anyone could look up what the default root password was, and if this is an IoT device that was going to be deployed and users, say, didn't have to know anything about Linux, you would either have to tell them how to change the root password, or you need to come up with some other script or something that says, assigns a default password that's maybe the device ID or a serial number or some hash like you would see on a lot of routers, and then say put a sticker on that device. That way you could only access the device if you have physical access to the device. This is to prevent things like people hacking IoT webcams because the default root password is just out in the open. Since I'm not going to get into best security practices here, this is a good way to work on developing your device. Just make sure you change this password prior to deploying this device in the wild, unless of course you want this to be some kind of development board that people are supposed to change and hack. But for an end user consumer electronics, you probably don't want to have a root password that's in plain text just floating out on the internet somewhere. The other thing you'll notice is that I can split variable assignments between lines. This could be on one line, but in order to have it split among multiple lines, if you wanted to have, say, different commands that are called user mod, add group, change group, whatever, you can use these backslashes to terminate the line, but say, hey, there's still a command on the next line. And you'll see this in many recipes throughout Yocto. Now that we're done with this, let's save and exit. With our custom image created in our custom layer, let's head back to our build directory. Here, we want to modify the conf bblayers.conf. And if you remember, back in one of the earlier episodes, this is how we add layers to our build process. This is where we're constructing the cake that's going to be bit-baked. If you remember from that earlier episode, this is where we added this meta-st stm32mp bsp layer. So we're going to go to the end of this line, hit A to append, and we are going to add the location of our new layer, which is home, my username, projects, Yocto, and meta custom for me. That is the location of the directory that contains our layer that we just added. We're going to exit out of this. A problem I ran into earlier when I was testing this is there is a variable assignment that conflicts with our default root password. We can find this conflict in image features. This is a variable that's part of our entire layer stack, and we can look for particular variables or names throughout the whole bitbake process by using this bitbake-e command and then searching or using grep for this particular name. This is going to fire up bitbake, and it's going to locate all of these variable assignments for me. You can see that this image features is assigned this debug tweaks name. This is something that's defined by default to help people debug when they're first creating an image. When you go to deploy, you will generally want to get rid of this assignment because debug tweaks allows you to do things like log into the root user with no password. Unfortunately, what I found out is that if you try to assign a default password like we just did with Tor, this assignment conflicts with that assignment and things will break. What ends up happening is you can't log in at all. It doesn't allow you to log into your image with no password, and you can't use your default password either. They just conflict with each other. I found that this variable is located in the local.conf file in the build process. So when we created this build directory, by default, it sets this variable. So we need to go in here and modify it. In VI, you can search for things by hitting /, and then let's look for image features. The extra image features, it looks like it appends to it, maybe? I'm not entirely sure how this works. But if we scroll down, you can see that, oh, you can assign debug tweaks here, which is not what we want. So we are going to comment this line out, which soft assigns this debug tweaks to extra image features. For insert, we're going to insert a # here to comment out this line. Then we're going to save and quit. And we want to run that bitbake-e grep for image features again to make sure that the image features variable no longer contains debug tweaks. And sure enough, if you look here, image features is now empty. Even though we changed the extra image features variable, it looks like somewhere along the lines in our local.conf, this somehow gets added to image features. So you could assign image features somewhere in your own recipes somewhere, and then extra image features might append it. I'm not entirely sure how that process works, to be honest, but by commenting out extra image features no longer contains this debug tweaks, which is exactly what we want. At this point, we are ready to bitbake. So instead of calling bitbake core-image-minimal, we're going to bitbake our own custom image because we added that layer, which contains an image. So bitbake custom-image is the name of our particular image. So let's go ahead and run that, and if it all goes well, hopefully our image will be baked, or in this case, created. It's going to pull in the various layers, including the board support package layer, as well as our custom layer, and apply any changes to the variables that we made. You can set priorities on the layers, which we didn't get into. That determines which layers get called first or take priority over other layers. And there's also ways to append or change variables, kind of like what we were looking at. You can soft assign some variables, and you can hard assign some, and you can also append with like a += to add lines. So you could have debug tweaks, and you could also add things to image features. So we could say debug tweaks, and then maybe in your own recipe, you add something else to that. We're gonna look at doing that in later episodes, but know that by modifying the variables, that's part of the bitbake tool. That's how you can tweak and modify your own custom image and other features about your own distribution. So I'm gonna let this run, and we're gonna come back and flash it to an SD card and see if we can now log in with our custom root password. That's now part of our custom image. Hopefully this process didn't take as long as the initial build, as it just needed to change a few things in the root file system, like make it bigger and create a root default password. You can see here that it only reran a few of the tasks to do that, and this process should have been a lot faster. For me, it was maybe 15 minutes. Let's head to our output directory, which should be temp deploy images and stm32mp1. If we list the files in here, you should see that a number of new image files have been created with our image name, custom image. These should exist alongside our core image minimal image files, so you have the option of flashing both. You could delete these if you no longer need them, but for now we're going to be using the custom image files to create our SD card. Something else that you'll find in here is a manifest file. This contains a list of all the packages in our image. We didn't add or remove any of these, but if you add a package, looking at the manifest file is a good way to see if it was included in the build process. BusyBox is the collection of user tools that we have available to us that allows us to do things like VI, cat, ls, when working with the operating system and with the file system. You can scroll through the list of available packages, and for our very small minimal build, you'll see it's not a whole lot, a couple dozen. We don't need to do anything with this, so we'll quit out of that. We need to flash the SD card, so I'm going to plug the SD card into my host computer. Hopefully that will enumerate as some drives with partitions that we created last time. I'm going to go ahead and unmount both rootfs and bootfs partitions. Then we're going to do DD just like we did last time. This time we're going to do it on the custom image instead of the core image minimal. This should be the ext4 file, and our output is going to be dev mmc block 2 partition 5, and we're going to do a BS of, or a block size of 1 megabyte. When that's done, we could probably go with this as our bootfs has not changed. However, since we're going to be modifying the kernel in future episodes, I recommend getting in the habit of burning the boot file system anyway. Remember to put the boot file system on partition 4 of our SD card. You'll see here that bootfs is named with st-image as it has not changed, and it doesn't really have anything to do with our custom image. Once that's done, remember every time we flash a new boot file system, we have to change the extlinux.conf file in that. To do that, I'm going to unplug and replug in my SD card. And I'm going to use sudo, since I have to do this with root privileges, vi media sgmustadio. It's in the boot file system that's now mounted. It's mmc0, extlinux, and extlinux.conf. We're going to change the location of the root file system. So delete the assignment, and we're going to press I for insert, and we're going to change this to dev mmcblk0p5. That should be the location of root file system. Hit escape, :WQ to save and exit. And we can either do this the easy way or the hard way, and I'm going to do it the hard way, where I'm going to unmount media sgmustadio. We're going to unmount the boot file system, and we're going to unmount the root file system that was also auto-mounted. I'm pretty sure that the umount command also syncs the drive, so you either want to sync or make sure that you're calling umount so that everything gets written to that file system before you pull out the SD card, or you might lose some changes, or worse, corrupt the whole SD card partition. Let's pull out the SD card, and I'm going to plug it into my STM32MP157D-DK1 development board. Let's open a new tab, because we're going to use the new tab to picocom into the board. And here, I'm going to get rid of that really long string, and I'm going to do picocom baud rate 115/200, and that should be on dev tty acm0. So let's open that up. Now that the terminal is ready, let's apply power to the board, and with any luck, we should see the boot process happening with our boot chain. If we made the correct changes, the root file system should be found and mounted. You can notice here that looks like the Ethernet package or module does come and auto loads as part of this board. That's probably set in the board support package somewhere. That is good to know. Networking comes by default with the board support package, so you can either use it or feel free to find a way to disable this module so that maybe booting happens a little faster. And that's where you get into trying to make Linux boot as fast as possible. You hunt down these extraneous things like, oh, I don't need Ethernet, so we find a way to get rid of this module in Yocto. I don't need USB, get rid of that module. So it's booting with the bare minimum, just needed to run your particular application. And that not only makes it boot faster, but ideally creates a more secure environment because there's less vectors for people to get into because there's no module in Linux to run any driver code. At this point, let's log in. So our login name is root. With any luck, we'll be asked for a password, and it should be TOOR, which is root backwards. And we're in. So that means our process of changing the root default password worked in Yocto. And now let's do a df-h. You should see the size of the root file system, which should be a lot bigger than 8 megabytes because we set it to 200 megabytes or mebibytes. As I mentioned, it's not exactly 200 megabytes, simply because of how the build process determines what's needed for the root file system, and it tries to make it as close to that root file system size setting as possible, but some things get moved around, maybe sector boundaries, and maybe some of the packages take up some room and it goes, oh hey, we actually need things for this temp file system that gets tacked on. To be perfectly honest, I'm not entirely sure how this size is exactly calculated. I'm sure you can find out in the Yocto manual somehow, but for now, it's a good place to start if you want to expand the root file system to take up more of your SD card to give you space to load things like custom applications. Now that we know that everything works, let's shut down. And I did not do this in previous episodes, and I recommend doing this whenever you're working in Linux to make sure everything shuts down, all your files and drives are synced so that you don't corrupt any file systems. I would say most of the time you're generally okay, but just to be sure, let's say shut down now. This will unmount everything, shut down any ports, drivers, and whatnot. Give it a few seconds, and from there we can remove power from our board. I hope this process helps you see how to create your own custom layer and start writing recipes to create your own custom Linux image. We will use this custom layer in the next episode when we go to enable an I2C port. See you then!